Hello, everyone. So I'll be talking about some profit inequality problems with correlations and augmentations. So this is joint work with Nicole Immorlica from Microsoft Research and Bo Waggoner from the University of Colorado. And here are their smiling faces. So let me start off with a simple motivation. So what if, imagine you are in a situation where you want to buy a house. There are a bunch of houses in the market, but the difficulty is that you don't know their values. So you get to see their values one by one. So maybe you see the first house, it has some value. Maybe you decided not to buy it. And as soon as you discard it, this house is gone off the market. So it's not available to you. Maybe the second house also you discard it. The third house, maybe you get to see its value, some xi, some real number. And you have to, again, decide immediately, are you taking it or not? So the goal of your algorithm is to decide if it's being revealed these house values one by one, whether it wants to take it or not, and it only wants to buy one of the houses. And the main challenges are, this is an online problem. You don't know the values of the houses upfront. And there might be even correlations between the values of the houses, just because there are many common features, maybe their size and like many other things. So what's at high level that message of this talk is that when there are no correlations, simple threshold algorithms are known to work pretty well. For example, in the extreme case, had I known all the values of the houses upfront, I would have just set the threshold of like the highest value of this house. So I'll pick the first house, which is higher than the threshold, which will perform very well. But in general, like for correlations, what we'll see, like in our models, like this threshold algorithms don't perform well. Instead, they can be made to work if you remove some of the options. So we'll get to it, like how it works. But let me first start off with a simpler question. Let's say, like, what if these values were independent? And I have to do this online selection. Can I hope to do anything even in this setting where I have this online selection, but for independent values? So this leads us to the popular profit inequalities model, where you have, think of these, you have n independent random variables, which are drawn from some independent distributions. So xi is being drawn from some known distribution fi independently. So think of this as like the value of the ith house. And you go to these houses one by one, you get to see the outcome, xi, and you have to immediately decide again the same question, am I taking it or not? And you need to just take one of them. Your goal is to maximize your reward. In particular, how well can you do as compared to the maximum offline solution? So offline is like, had you known all these xi's upfront, you would have selected the max xi. So what fraction of it can you get? And an amazing result, like what we know is that these simple threshold algorithms, where you tick the first item which is above this threshold. In fact, even if you set very natural thresholds, which is say the mean or the median, both of them are known to work and they give you a 2 approximation. In fact, this 2 approximation is tight as well. You cannot do better than this in general. So that's nice because these algorithms are very easy to run. And there are even many extensions, no? In particular, suppose like rather than suppose you were buying one house, you were buying R houses. That makes the problem easier, because you have somewhat more flexibility and the approximation ratio starts tending towards 1 as R becomes larger. This was a result of Sahil from 2011. People have also studied matroid versions of the problem where you can get a 2 approximation. There are many, many other variants. I'm not citing papers, like these are results on packing constraints, arbitrary, and many other settings. Good. So, but now we want to handle, like this answers the online selection problem, but in the case when the distributions are independent. But what if the values are correlated? Unfortunately, there's a hardness result of Hill and Kurtz from the 90s that shows that in general for arbitrary correlations, you cannot do much. So you have to basically lose a omega n approximation factor, which is pretty much like selecting a random house, a random item. So, okay, now how can we go around this? So this leads us to the linear correlations model that we study in this paper. This was proposed in Bateni et al., who were generalizing a model of Chawla et al. On common base value models. So what's the idea in this linear correlation model? You have these x1 to xn, these are the values of the houses, but now they need not be independent. So these are being revealed to you one by one, x1 to xn as before. There are also some features, which are some independent features on which these variables depend. So what are these features? These features could be like the size of the house, how much you value the size of the house, or many other things. So these are some independent features, which will determine this x. In particular, it will be determined using some linear matrix. So you have a matrix A, where Aij entry belongs to 0 to 1 and determines how much xi is affected by variable yj. So notice y1 to ym are independent, but x's need not. X's will in general have correlations. So the model is that this vector x is nothing but some known matrix A times vector y. So the crucial thing is this matrix A is known, and the distribution y is also independent. So from known distributions, your algorithm gets to see again x1 to xn. It never gets to see y1 to yn. It only gets to see them in some sense indirectly via x1 to xn. And as soon as you get to see xi, you have to immediately decide whether you're taking it or not, and you have to only take one of the options. So just as examples, like if A is the identity matrix, you basically go back to the profit inequality problem because xi equals yi, and it's independent because all yi's are independent. But there are other models as well, like what if this matrix A is just a 0-1 matrix, which means like some items, an item is affected or not at all affected by a feature. So one can study many of these variants. And the question is, okay, can we get a constant approximation in this setting, in this linear correlation, which is a limited kind of correlation, but it still captures some interesting applications. So one parameter which we'll see will be of interest is the sparsity of this matrix A. So the row sparsity is the maximum number of non-zero entries in a row. So in general, this is a large n by m matrix, but maybe for some applications, your row sparsity or your column sparsity could be small. Maybe each value of the item only depends on a few features. So in which case you might expect the row sparsity to be small. So what's our main results, our technical results? So first, in the single item case, when you're selecting just a single house, we get a min of the row and the column sparsity approximation. So in fact, this is even tight. So if either of your row or the column sparsity is small, you can get that approximation factor. And in general, you cannot do better than the min of these two. Some remarks that, I mean, as I was saying earlier, like threshold algorithms don't work well. In fact, they perform very, very bad in omega and approximation. But under some special matrices, as I was saying, like when this matrix is a 0-1 matrix, then they can perform well. But general matrices A, when there are like non-zero-1 entries, then they are bad. We also have results for selecting multiple items. In particular, if we are selecting R items, then interestingly, there's a difference between column and row sparsity. The results are in some sense no longer symmetric. If your rank, this R, is much larger than the column sparsity, you can get some approximation factors tending towards 1, which is somewhat similar to what we are getting in the profit inequality problem, the independent case, as R becomes large of Sahil. But if R is much, much larger than only the row sparsity, then yeah, then it's not necessarily implies much. So good. And the main ideas of our proofs will be again to use some kind of threshold algorithms, but we call these inclusion threshold algorithms, where you run a threshold algorithm on a subset of the items. So we'll basically select a random subset of the items on which we'll run this threshold. So we'll have to be a little careful depending on the application, like how we select this random subset, but that's what we'll do. And then we'll also prove some augmentation lemma, which are some kind of robustness. I'll get to it in a bit. Good, so what's the outline? Like I just told you the model, profit inequalities with linear correlations. Now I'll give some examples and explain what are these threshold-based mechanisms and what's this augmentation problem. And finally, I'll tell like how we obtain these single item and multiple items results. Good. So first, let's start off with an interesting example, which shows why these threshold mechanisms, the simple threshold tau mechanisms, don't work well. So we call this the tower instance. So in fact, these threshold mechanisms work bad even when the both column and row sparsity is very small, even sig2. So what's the example? So remember, like we have these y1 to ym independent, and x's are the ones of which we will be seeing, and they depend based on this matrix A. So what's the connection? So xi depends on yi plus 1 over n. So it just depends on two random variables, yi and yi plus 1. In particular, it's like yi very affects it a lot, but yi plus 1 only mildly affects it. And what are the distributions of these yj's? Each of them take a very large value with a very small probability. So n to the j with probability n to the minus j, otherwise that's 0. So that's the distribution. And as you can see, like both the row sparsity and the column sparsity is only at most 2. Good. So now let's try to compute what is the optimal solution, expected max xi, and what are threshold algorithms doing here. So first claim is that the expected max, which is the opt, is pretty large. It's omega n. This is because each xi is greater than yi. So this inequality is true. And because these random variables are non-zero with a very small probability, expected max yj is pretty much the sum of the yj's expected, which is omega n. However, if you design any threshold algorithm, one can show that it doesn't get too much value. It only gets at most like a constant value, 1 or 2. The rough intuition is, if suppose you set a threshold which is close to n to the j, it gets you only values when like yj is when yj is active, which in expectation gives you only value 1. In all the other situations, for all the other j's, it pretty much gives you 0 value. That's the idea. I mean, so one can do this calculation. Okay, so this defeats simple threshold-based mechanisms. So what's our idea? So the main subproblem that we go through to solve this profit inequality with linear correlations is an augmentation problem. So it's an interesting problem by itself, and it's a generalization of profit inequalities, where you think of each random variable consisting of 2 parts, an independent part and a dependent part. So think of each xi has an independent component z and a correlated noisy component dependent part. It's correlated with the past. This is always positive. So think of it in the following way, that actually you wanted to solve the problems for z1 to zn, these independent random variables, but somehow you are getting a noisy version of each of these random variables. So you're getting to see xi's. This noise is always positive. So ideally you should expect that it should only help you. You want to get the value which is close to expected max of zi. So your hope is that this noise only helps you, but does it? I mean, maybe your algorithms are not so robust to these noises. So that's what you want to study. In the extreme case, of course, if these noises are 0, you get back to the profit inequality problem. Here's an illustrative example. Imagine you have just 2 random variables where x1 is uniform between 0 and 1, and x2 takes a pretty large value with some small probability. In particular, the expectation of x2 is very large. It's, in this case, say 100. The expectation of x1 is very small. So max is pretty much expectation of x2. Now, what does the median and the mean thresholds do? The median threshold will be pretty much a half, because half the times this x2 is pretty much 0. So you'll set a threshold of roughly close to the median, which will select x1 half the time. Mean threshold, on the other hand, sets a threshold of around 50 because mean is very large. Okay, so this is good. So both of them will give you a half approximation to the expected max xi. But now let's see what happens if I add slight noise. So I'm adding a slight positive noise. Suppose x2 remains the same, but in x1 I add a slight noise. I add a deterministic number plus 2. Interestingly, now if I still run the median threshold algorithm, which was setting a threshold of half, it's always going to pick x1, because now x1 is always above half, which is bad because now you're not getting x2 ever. You're always stopping at x1, whereas most of your actual opt was coming from x2. So this shows like, okay, you need to be careful. Not all threshold algorithms are robust to positive noises. So median threshold fails. Interestingly, mean threshold works out fine, which raises a question: are mean thresholds always robust, or was there something magical about this example that made them robust? And what we show actually is that, okay, actually mean thresholds are always robust to positive noises. So in particular, if you set a threshold which is expected max of zi over 2, which is the mean of the independent zi's, then you get expected alg, which is at least expected max x zi over 2. And the proof is also very easy. It's pretty much the old proof, how we do profit inequalities. So you don't need to go over the details, but all I'm saying is it's a very short proof, which is pretty much just repeating the old proof for profit inequalities by their work, give you 2 approximation. And you can one can easily verify that each of the inequalities go in the right direction. So these dependencies don't hurt you. However, they do hurt you for the median threshold. Good. So now what's the idea for our column and row sparsity results for the single item? So the single item column sparsity result, let's recall it was, so I was getting a min of column sparsity and row sparsity approximation. Let's separately first obtain an algorithm which gets you column sparsity, and then we'll do a row sparsity also. And in general, we'll get the min of the 2. So column sparsity means each column is sparse, maybe at most 3 non-zero entries, but some rows could be very dense. So this is equivalent to saying like each yi does not affect many of the xi. Okay, so what's our algorithm? Our algorithm is kind of intuitive, at least in hindsight. Is what you do is just ignore each xi independently with a pretty large probability, 1 minus 1 over this sparsity. Okay, so now I'm going to just ignore most of the xi's. Now look at each of the yj's. Look at the first surviving xi in which it belongs. So the crucial thing is Yj does not belong to too many xi's because the column sparsity is small. We are thinking of SCOL. So assign Yj to the first surviving xi, which is not getting ignored. And this defines Zi. So Zi is defined as summation of Aij Yj to where I'm taking the sum over j's which are assigned to I. The important property is that this Zi is independent of all the past. So I can apply the augmentation lemma. This is independent because notice all the Yj's, they are appearing for the first time here. They did not appear anywhere before because I've ignored some of those xi's. Now the algorithm, now from the last slides, we know that, okay, this augmentation lemma will give us a value which is pretty close to the expected max Zi. Now it suffices therefore to show that expected max Zi is close to expected max Xi up to this approximation factor that we are aiming for, which is the column sparsity. And this is also not difficult just because the maximum Xi, whichever is the real optimum solution, that has a decent chance of surviving 1 over SCOL. So you'll get a 1 over SCOL factor. And also then given this, each Yj which belongs to Xi, it has a decent chance of actually being assigned to the same Zi. This is just because most of the Xi's in which it appears, they will get disappeared because I'm disappearing them with probability 1 minus 1 over SCOL. So that's how it works out. In case you get lost, I mean, the high level idea is just to run, like randomly discard some of the variables and just apply this augmentation lemma. And the same idea also works even for S-row approximation. But one has to be a little more careful how one discards these random variables. So I won't go over this detail because like the trick comes because some of these AIJs could be really, really small. So it does not help by just randomly discarding. But we are able to construct some dependency graph based on which if we carefully ignore some of these variables, then one can still argue that, okay, each Yj is surviving with a decent chance, and then you can apply the augmentation lemma. Good. So let me just briefly tell about the multiple item results. So the multiple results items are again, as I was saying, we can get a nearly one approximation for R being very large. And this proves also goes via similar idea. You basically need some kind of an augmentation lemma that your algorithm is robust to these positive noises. Unfortunately here, we cannot just directly apply previous work. Like earlier we had a mean threshold algorithm. So existing algorithms don't work, but we are able to design a new algorithm which is actually robust to these noise. This is based on some concentration inequalities where we first partition the entire number line into disjoint pieces and then apply some concentration and put some thresholds within each bucket. Good. So to conclude, so we studied these profit inequality with linear correlations model, where we have this linear dependency on these independent random variables, where we have both results for single and multiple items. The main techniques are inclusion threshold algorithms and algorithms which are robust to augmentations, these positive noises. Some cool open problems are, okay, what are the tight optimal approximation ratios? So this is tight up to some constant factor. So can we even nail down this constant? And can we extend these results to late rate constraints? That's another interesting question. Thank you.